Okay, let's do 3 short examples that will help you make sense of error terms for Taylor polynomials. So the idea of a Taylor polynomial is it's a couple of terms from a whole Taylor series that you can use to approximate a function. So here's the whole Taylor series for e to the x. This is a Taylor series centered at 0, so it's really the Maclaurin series. We'll use a third degree Taylor polynomial, so that's all of the terms from the series up to the third degree term. And all of the rest of the infinite terms we'll call the remainder for the third degree Taylor polynomial. And you denote that with r sub 3. All right, so this term describes the error if you use the third degree Taylor polynomial to approximate a value. And it makes sense why. If I plug in an x value, because I want to know what is e to the x at like x equals 2, if I evaluate just these terms at x equals 2, that's not going to give me the real value for e squared, because the real value also includes these other terms over here. So if I only include these first terms here, what's the error? The error must be the sum of all of the rest of the terms. So that's why we call that the error term. All right, so what if we are only going to evaluate x values between -3 and +3, and we want to know what is the maximum possible error if we're going to plug in values in that interval if we're using, oh, you know what, it's too many 3s. Let's do it with 4 so that we're less confused. Let's do it with 40. That's really big. All right, so x is between -40 and +40. What's the maximum error? So I know that this is the error term. So you could try to calculate the error term by figuring out what is this infinite sum. But you don't have to. This is where the Taylor Remainder Theorem comes in. The Taylor Remainder Theorem says that this entire infinite sum is the same thing as this equation right here. So what it says is the infinite sum is the same thing as the n plus first derivative of your function evaluated at some number c divided by n plus 1 factorial times x to the n plus 1. It makes sense that x should be in here because your error is going to depend on what x value you're trying to approximate. If your x value is really far from the center of your series, you would expect the error to be much larger. Okay, what is this mystery value c? This theorem comes from the mean value theorem, which guarantees that there exists a certain value that has certain properties. So the idea is you can prove that there exists some number c that makes this equation true, that makes this equation the same as this infinite sum. But it doesn't really tell you how to find which number makes this equation equal to the sum. So instead of trying to find the number c, instead we'll think, what is the largest this error term could be? And then we'll guarantee that the error is smaller than whatever that largest value is. So in our particular case, we're looking at the third degree Taylor polynomial. So our n value here is 3. So if I want to evaluate what is r sub 3, that's the same thing as the fourth derivative of your function evaluated at c divided by 4 factorial times x to the fourth. So let's think about what would make this error term as large as possible. Well, it depends on what this number c is and what this number x is. First, let's figure out what is the fourth derivative of our function. Our original function was e to the x, so the fourth derivative is also e to the x. And when we evaluate that at c, we have e to the c. Divided by 4 factorial is still there, and x to the fourth is still there. All right, what do we know? We know that x, we said, was going to be between -40 and +40. And we also know that c is between the center of the function, which is 0, the center of the series, and the x value. So c is going to be between 0 and x. So if we think about plugging in numbers, what x value is going to maximize this expression? It seems pretty clear that the larger the x value, the larger this term will get. So x equals 40 will make this term as large as possible. Same thing with c. when c equals 40, it seems like this term is going to be as large as possible. So what we know is if we plug in 40 for c and we plug in 40 for x, that's going to make the error term as large as possible. So we know that the error for our approximation has to be less than whatever that is. In this case, it is extremely huge because the center of our function was at 0, and x equals 40 is a really long way from the center. So if we're just using a couple of terms as an approximation, we would expect the error to be quite large.